Okay, so in the last two classes, we built up the notion of having manifolds and maps between manifolds, and also the notion of a push forward of a vector and the pullback of dual vectors. Okay, and we saw if the mapping is diffeomorphism, then you can have you can also in some sense pull back vectors and push forward dual vectors. So the other thing that we saw is that if you have a manifold M, okay, with some vector field, say X, one vector field, you just need one vector field, then this vector field X generates a one parameter family of diffeomorphisms. Okay, you can think of it as a flow field, which generates a flow. So let's say if X corresponds to this magenta lines shown here, then X generates a flow where this point moves sort of to this point and so on. Of course, the amount you flow depends on a parameter T. Okay, so it's a one parameter flow. And so we denoted the flow, let's say generated by X, as some sigma Tx. And if you have another, so today we're going to consider two different flows. So if you have a field X, it generates one flow. If you have another vector field Y, it generates a different flow. Okay. And so if we denote sigma Tx as the flow generated by X and tau of Tx as the flow generated by Y, we've seen in coordinates that if I want the coordinate sigma mu Tx, this can be found by just exponentiating. So you get this operator exponential T X, where X is the field, okay, evaluated at the point X, acting on X mu, or equivalently acting on sigma mu at the point where T is equal to 0. Okay, where you're assuming the flow starts at some point X mu. Okay, and then you flow for a time in quotes. Okay, this parameter T. Okay, you flow for that amount of time, and you follow the flow. You follow these velocity lines. You follow the streamlines of the flow. Okay, and then you reach a new point, and every point does this. So this is a diffeomorphism of the manifold itself. So so we now imagine that sigma Tx is one flow which is generated by the vector field X, and tau Tx is another flow generated by the vector field Y. Okay, and as I just mentioned, sigma Tx is a diffeomorphism. So if I fix the value of T, then this is a map from every point X on the manifold to another point X on the manifold. It's a diffeomorphism. Okay, it's also invertible by reversing the flow. Okay. So under the diffeomorphism, we can find the change in the vector field Y at some point X. Okay, so what we can do is we can consider the flow due to the field X. So we consider the flow due to X. And when we flow due to X, we can now compare what happens to the change in the vector field Y as we flow along X. Okay, so here's the idea. So let's imagine that we're at the point X. This is the element of X, capital X, at the point small x. Okay, and so this is the vector field capital X at this point, and we flow an amount epsilon. Okay, so we flow from this point here to this point here. We flow in the direction of capital X. And what this does is it takes us to a new point, which is sigma epsilon of X. So sigma being that map, okay, which is the flow map. So we flowed by an amount epsilon, and we started at the point X, and we end up at this new point, sigma epsilon X. Okay, now what we want to do is we want to compare. Okay, what we want to do is we want to compare the original Y, which was at this point, okay, with, well, roughly speaking, we want to see what the change in this Y is after the flow. Okay, but the point is that we can't compare directly the Y at this point and the Y at this point because these live in different tangent vector spaces. Okay, they live in different tangent vector spaces. However, okay, we have seen that since this map is a diffeomorphism, then the inverse map also exists, that is sigma minus epsilon, which will take us back, okay, from this point to this point, that is sigma, so if I apply sigma minus epsilon on sigma epsilon of x, I will just get back to point x. Okay, I will end up here. So now, since this diffeomorphism means that sigma epsilon is invertible, that is, we can find the map sigma minus epsilon. Okay, what that means now is that we can sort of push forward this vector y sigma epsilon x. Oops. We can push forward this vector y sigma epsilon x and see what happens to this vector when we push it forward here. Okay, so this is the push forward of y sigma epsilon x under the map sigma minus epsilon. Okay, so in other words, this vector here is y sigma epsilon x under the push forward by sigma minus epsilon, which we denoted as sigma minus epsilon star. Okay, and now this vector, okay, which is the push forward of this vector can be compared against the original y. Okay, and we can compare the difference between the two. Okay, since the diffeomorphism is invertible, I mean, in some sense, of course, we are only pushing forward, but we're pushing forward in the reverse direction. So we can think of this as sort of a pullback of the vector. Okay, remember the pullback of a vector is only possible in this sense. Okay, in the sense when you have a diffeomorphism. Okay, so since we do have a diffeomorphism, okay, we can sort of pull back this vector. Okay, or push forward this vector using the inverse diffeomorphism. Okay, and what we're going to do now is we want to compare this. Okay, the pullback or the push forward in the opposite direction. We want to compare that with the original y of x. Okay, the pullback of this with y of x. So this will allow us to define a derivative. Okay, it's the difference between this pullback and the vector y of x. Okay, this difference you expect it to be small, to be order epsilon, right? Because in the limit epsilon goes to 0, you don't expect any difference because you're not really moving from this point at all. So, so to leading order, this difference should be order epsilon. So then I divide by epsilon and take the limit epsilon goes to 0. This defines for me something called the Lie derivative. Okay, this is the Lie derivative of the field vector field y by the vector field x. Okay, so you have to specify two vector fields, one that I'm taking the derivative of. Okay, and one specifies the direction along which I am differentiating it. Okay, and of course I have to specify at which point. Okay, so here this is evaluated at a point x, but we leave this point x implicit. Okay, this derivative can be taken at all points on the manifold. Okay, so this defines the Lie derivative of the vector field y along the vector field x at some particular point small x. Okay, so we'll see explicitly how to evaluate this in terms of coordinates. But before I continue, any questions here?
Sir, can we define it in other way, like keeping the y sigma x and then push forward to the y and comparing? I mean, here we use the pullback operator. Instead of this, we can use like y sigma epsilon x minus and the push forward of this y vector at that point.
Right, so that's a good question. So what if we defined it by pushing forward this vector, right? And then comparing the difference between this and the push forward.
Yes, sir. Will these two be equivalent? Or
yeah, the answer is yes, they will be equivalent. Okay, it's not obvious, but you can show that they will be equivalent. When we work it in components, it'll actually be very obvious.
But sir, like if we do that, then the Lie derivative is actually being evaluated at sigma epsilon x and not at x, because
again a good point. but again, in the limit that if we're looking at smooth functions, once you take the limit, then x and x plus epsilon are really the same point. So it doesn't matter whether you evaluate the derivative at x plus epsilon or at x. In the limit epsilon goes to 0, you're still evaluating at the same point. Right? In a sense, for example, supposing I take the derivative f, so supposing I evaluate the derivative of f at x, okay, just a regular function. We know that we can do this, right? And this evaluates the derivative, limit epsilon goes to 0. But now suppose I evaluate the derivative at x plus epsilon. So what I'm doing is this. So I'll write it as I'll evaluate the derivative at x plus epsilon minus f at x plus epsilon divided by epsilon. Okay. In the limit epsilon goes to 0, these are the same thing. If the function is smooth.
Okay, sir.
Okay, I mean visually you have f of x, you have x, this is a function, this is the derivative at x plus epsilon. If the function is infinitely smooth and differentiable, right, then the derivative here and the derivative here is continuous, and in the limit epsilon goes to 0, I mean it's really the same derivative that you're sort of evaluating. Okay, the tangent can't change drastically, right, for a vanishing displacement. Okay. So now what we're going to do is we're going to study the incompatibility between two flows. Okay. So this we've defined a Lie derivative. We've differentiated y along the flow generated by x. Okay. So what we've done is, so suppose you have the point x, okay, and then the so the magenta line denotes the flow generated by capital X. So small x will move along this curve, okay, as I flow with the vector field capital X. So let's say I move to x prime, okay, which is sigma epsilon of x. So that's this point. And now we have the two vectors. We have the vector y at x. We have the vector y at sigma epsilon x. Okay, and these themselves generate a flow. Okay, so this is generating a flow, let's say, which we call tau tx, and this is a flow tau tx prime. Okay, this is the flow starting at the point x prime. And now what we're doing is we're pulling back this vector, or we're pushing it forward using the inverse map, sigma minus epsilon star. Okay, so we're pulling it back to this vector, sigma minus epsilon star y, the y which was at sigma epsilon of x. And we're comparing the difference between this, okay, which is a vector at x, and this vector. Both of these are vectors at x, so we can compare them. Okay. So coming to the question that Pravesh asked, okay, so this difference between this Lie derivative, so the way we've defined it is the pullback of this vector y sigma epsilon of x minus y of x divided by epsilon. But I could have equally well defined it by looking at the point sigma minus epsilon of x. Okay, and I could have looked at the vector field y at this point, and I could have pushed this forward, okay, using the regular flow sigma epsilon, okay, sigma epsilon star. So I could have used sigma epsilon star, taken the vector field at sigma minus epsilon, pushed it forward, okay, and then compared it with y of x. Okay, or alternatively, I could have taken this vector, okay, and pushed it forward and then compared it with this. Okay, and that would be y sigma epsilon x, which is this, okay, from which I subtract off the push forward of this, which is sigma epsilon star y of x, okay, divided by epsilon. All three definitions are equivalent. Okay, if you have smooth vector fields, all of these are the same. Okay, there's no difference between them. Okay, so now what we're going to do is we'll work out, okay, the components of Lxy. So obviously, since this is a difference between two vectors at the point x, the Lie derivative results in a vector at the point x. Okay, so the difference of these two vectors is again a vector at the point x. So what we're going to do is we'll work out Lxy and we'll work it out in a particular coordinate chart. Okay, so we'll assume that this point x is in some coordinate patch u, okay, with phi being the coordinate map. Okay, so we'll not be too pedantic about being explicit about putting in phi and so on. Okay, we know what we mean when we say this point has coordinates x mu. Okay, and so let's imagine that the vector field x, okay, expressed in this coordinate basis is x mu partial x mu. So these x mu's are functions of x. Okay, and similarly, the vector field y is y mu partial y mu. Sorry, y mu partial x mu. Okay, because it's the same coordinates on the same manifold. Okay, and these are again functions of x. Okay, now we know that after a flow, this is what we showed last time. Okay, is that the point x mu will now move to the point sigma epsilon of x, and sigma epsilon of x will have coordinates. Okay, that is sigma epsilon x mu will have coordinates x mu plus epsilon times capital X mu. Okay, right. So now what we want to do is we want to evaluate. Okay, in order to evaluate this derivative, so we'll use our definition. So we want to first evaluate what is y, okay, of sigma epsilon x. Okay, that what is y at this point. Okay, not y at x, but what is y at this point. So y at this point is y mu, but not evaluated at x, but evaluated at this point. Okay, sigma mu x. So it's y mu of x nu plus epsilon x nu of x, where this is evaluated. So again, these basis vectors are basis vectors at the point x plus epsilon x. Okay, so if it's a derivative with respect to x mu, this derivative is taken at the point x mu is x mu plus epsilon x. Okay, and now what we do is we Taylor expand this for small epsilon. So we can write it as y mu of x plus epsilon x nu partial nu. Okay, y mu of x epsilon mu. Okay, that's a Taylor expansion. And where these e mu's are just partial x mu. Okay, and this partial nu is also partial x nu. Okay, so this is just y, but then we have to pull back this y. Okay, by using this, or actually we push forward using the inverse diffeomorphism. Okay, so how do we evaluate the push forward of a vector? Okay, using this inverse diffeomorphism. So suppose this vector is at x plus epsilon x. Okay, like this vector y. And if we want to push it forward, okay, using the inverse map or pull it back, whatever you like to think about it, we saw that you need to use the Jacobian of the transformation, okay, in components. So in components, you have to use partial x mu, okay, partial x, the the old coordinates, which are x plus epsilon x nu, okay, this acting on v nu. So it's a little bit, it's not very hard to show this, but you can work it out. Okay, it's easier to work out this derivative, okay, because capital X depends on X. And so when you work out this derivative, you get delta mu nu plus epsilon partial mu x nu. Okay, so this is the inverse Jacobian. Okay, this is the inverse Jacobian. If you call this the Jacobian, this is the inverse Jacobian. And so you need to invert this quantity. Okay, and that's what we want to evaluate here. And so if I have j mu nu, okay, the inverse Jacobian is j inverse, and I should have something like this. So the product of these two should be Kronecker delta, mu delta. Okay, maybe delta is a bad symbol. Sigma. Okay, so if mu and sigma are the same, then you get delta mu sigma. So it's quite easy to see, okay, or you can explicitly plug in and check, okay, that that the inverse Jacobian is just delta mu nu minus epsilon partial nu x mu. Okay, do not do this by just taking 1 by this. That doesn't make sense. Okay, for a particular delta mu nu, yes, I mean, even then, okay, that's not the right way to do this. Okay, you don't take a single component of this and then flip it over. Okay, that's not how you invert partial derivatives. Okay, what you have to check is that the inverse Jacobian times this Jacobian, okay, the product satisfies this property. Okay, and to order epsilon, you can quite easily see that that will be true. Okay. Okay, so sorry, these are some technical steps, but let's just go through them. Okay, so now what we want to do is we want to apply this inverse Jacobian, okay, to y sigma epsilon x to pull it back. Okay, so what we're going to do is we'll have, so I'll just write those components here. Y, so I'm going to write this using, I'll switch indices. So I'll call this new, call this new, call this mu, call this mu. Okay, and this will become new. So what I have is y nu plus epsilon x alpha partial alpha y nu. Okay. Okay, and now I have the inverse Jacobian. Okay, so which I stick in. Okay, so this inverse Jacobian is stuck in the middle. So it's delta mu nu minus epsilon partial nu x mu. Okay, and then I finally have my basis vectors, which are epsilon mu. Okay, evaluated now at x. Okay, now these basis vectors are evaluated at x, not at x plus epsilon, because I have pulled back, okay, to the point x. So now when you simplify all of this, okay, what you get is the product of these two gives you y mu, okay, at x. And then I want to keep the term still order epsilon. So I'll take this product and this product. Okay. And what that will give me is epsilon x nu partial nu y mu minus y nu partial nu x mu. Okay, and times e mu. Okay, at x. Okay, so this is the pullback of y. Okay, and now we subtract off y at the point x, which will subtract this off, divide by epsilon, take the limit epsilon goes to 0. That will just give us this. Okay, so in coordinates lxy is x nu partial nu y mu minus y nu partial nu x mu e mu, where these e mu's are basis vectors at x. Okay, at the point x where we're evaluating the derivative. Okay, so so this is the expression in a particular coordinate system. Okay, any questions about the steps here?
Sir, can you repeat this Jacobian part once again?
This Jacobian, the inverse Jacobian?
Yes, sir. From yes, sir.
Yeah, so what you need to check, so this is easy to evaluate, right? This is just delta mu nu plus epsilon d mu x. Okay. To evaluate the inverse Jacobian, you don't just, I mean, how do you evaluate the inverse Jacobian? So supposing I want to evaluate this quantity, how am I going to evaluate it? I can't just write this as, this is not, what sense does it even make to write this as 1 by delta mu nu? Okay, that doesn't make any sense at all. Okay, so what you need to do, okay, is that the Jacobian and the inverse Jacobian. So if I write this as Jacobian with an upper nu and a lower mu, I think of it as a matrix. Okay, so the nu index is like this, the mu index is like this. Okay, this is the Jacobian, and then I want to multiply by the inverse Jacobian, and the result should be a diagonal matrix. Okay, so this now is, let's say, the nu index, and this is, let's say, a sigma index. Okay, then what I have is J nu mu. Okay, and I have J inverse, and by the same logic, sigma nu. Okay, this should be equal to delta sigma mu. Okay, so this is right now the way I've written it. It looks like a guess. Okay, but we'll see that the product of these two will indeed satisfy this relationship. So if I take the product between these two, again, I have to be careful. I have to use different indices on the inverse Jacobian and the Jacobian because I'm not summing over the mu and sigma indices. Okay, so what I need to do is I need to replace one of these. So let's say I replace the mu over here by so let me see. Yeah, let me replace the mu by sigma. Okay, let's take the product of the two. So if we take the product of the two, and then we sum over the repeated indices, okay, that's basically equivalent to doing this multiplication, which is doing this. So we take the product between the product of the two deltas gives us delta mu sigma when I sum over nu. I'll keep only the order epsilon terms, which means I need to keep this term and I need to keep this term. So this term, when I take, it gives me epsilon partial mu x nu times delta sigma mu, which sets nu to be sigma. Okay, so it's this. And this cross term will set nu to be mu. Okay, so that will be minus epsilon partial mu x sigma. So to order epsilon, this is what I have, and these cancel out. So I just get delta mu sigma. So I can see that to order epsilon, this is the correct inverse Jacobian.
Sir. And sir, when you applied this sigma minus epsilon star to the b mu at x plus epsilon x, so one way is that we can use the definition of sigma minus. Uh, uh, Sir, where you have applied it at the vector v mu at x plus epsilon.
Here,
Yes, sir.
this formula.
Yes. So you have just written there del x mu over del x plus epsilon x.
Yes, this is the inverse Jacobian, which is here.
Okay. Is it the same that we apply sigma minus x minus epsilon x mu kind of like the definition of sigma epsilon and
Sorry, I didn't understand.
this sigma minus epsilon acting on v mu, we can write it like x minus epsilon x mu acting on v mu.
X minus?
Epsilon x mu. Yes, sir.
You mean this?
Uh,
Something like this is what you want to say.
no, sir. Without using this Jacobian, just using the form of this sigma epsilon. Is it the same thing?
What do you mean by using the form sigma epsilon? The only way we worked out sigma minus epsilon is by using the Jacobian.
Okay.
How else do you want to do it? I mean, what is the other technique you have in mind?
Like sigma minus sigma epsilon, when you apply on it some coordinate x, then it gives me x plus epsilon x mu.
No. This is okay. This is sigma minus epsilon star. It's not sigma minus epsilon. Remember, we're using the same notation for many things. F is the diffeomorphism. F star is the push forward map. F upper star is the push back map. Sorry, is the Sorry, this is the pull forward and this is the push back. Okay, these are different things. This is a map from manifold to manifold. This is a map from vector space to vector space. This is a map from dual vector space to dual vector space. You're thinking of sigma, which is a map from F to M. This is sigma star, which is this.
Yes, sir. Get it.
Okay, you can't do that, right? You can't use this to do anything with vectors. Okay, this of course induces such a map, but this is not the same thing.
Yes, sir.
Okay, yeah, I mean, there's a lot of concepts here which are condensed very quickly. I mean, it might have seemed slow when we're going through it, and now it's like, suddenly we're using all of these ideas together. I highly recommend that you go over those concepts again very, very, very carefully. Okay, this is very tricky. Okay, and it's very easy to get confused with these concepts if you don't go back and review them. Okay, especially because we're using the same index. So with F, you may not even notice the star hanging around here, whether the star is lower, upper. Okay, be very, very careful and precise about this.
Sir,
Yeah.
Sir, we like from sigma epsilon x, like which has coordinates x plus epsilon x, like we are going to x, so that is why we are using this Jacobian. But instead, like if we had used the thing that you wrote, like we would have got the same. Like if we use del partial derivative of x mu minus epsilon capital X mu divided by del x nu, that gives the same answer because it's.
Yeah, but this is not the right Jacobian to use.
Yeah, but it's not. But sir, from the definition, as you said, that they are all equal. So, is that the reason this holds? Like because I mean, though this is not correct, but like it's like we're going from x to x minus epsilon. But
Yeah, yeah. I don't know. I'm not sure if that's exactly from one of these alternate definitions. Yeah, I think what you would actually have to do is this. You take what? No, I mean, I don't think that's right. You can't use the Jacobian there. What you could have done is this, use this definition, right? Where you just use y sigma epsilon, but instead of pulling this back, you push this other one forward and then take the difference. In that case, the push forward will apply the Jacobian to the vector at x, okay? And that Jacobian does look like this, okay? But this, so if I'd use the alternative definition, okay, this third definition, then this would have still been your regular y at sigma epsilon of x, okay, which is y mu at x nu plus epsilon x nu. Okay, and this is evaluated at the point x plus epsilon x. And this would now, you would use the Jacobian, okay, and the Jacobian would be partial x. Something like this, and v nu or y nu. Okay, so this would be the push forward of this. But now with basis vectors, sorry, let me write these basis vectors as e mu. And again, these basis vectors are the pushed forward basis vectors, so they're at x plus epsilon x. So this is how you'd get a minus sign for this term, okay, because now when this I can differentiate. Okay, but there's no logic for just using something like this, okay, and sticking it in front of this. Okay, that works to order epsilon, but it's sort of accidental.
yes, sir, because it depends on like the left hand side also, like y mu evaluated at what point, like even in that. As you were writing that v mu was at x plus epsilon x, so we cannot use that Jacobian.
Yeah. Yeah, so do be very, very careful, okay, when doing this. I mean, maybe in some way it might be possible to see why an x minus epsilon x would show up, but you have to be very careful if you want to show that. Okay, now we've encountered this before, okay, and this is very similar to the Lie bracket that we had defined earlier. So let's recall what the Lie bracket was. So we're going to find this connection between the Lie derivative and the Lie bracket. So the Lie bracket was defined. So supposing I have two vector fields x and y, we define the Lie bracket of xy acting on smooth functions f to be y acting on f. Remember, y acting on f is just y mu partial x mu f. By definition, this is how we define vector fields, right? As directional derivative operators. So so this makes sense, okay? And this gives you a scalar function. And then again, I act on this scalar function with x. And I reverse the order of those operations. First I act with X, then I act with Y, and I take the difference between these two. Okay, that's how we define the Lie bracket of XY acting on some function F. And what we showed is that, I don't remember whether we showed it or not, but you can certainly show it quite easily, is that XY is a vector field. Okay, so this Lie bracket also behaves like a vector field. Okay, with components of this Lie bracket given by X nu partial nu Y mu minus Y nu partial nu X mu. Okay, and these are the basis, the coefficients multiplied by the basis vectors E mu. Okay, so basically this Lie bracket is the same as the Lie derivative of Y with respect to X. Okay, so the Lie bracket XY is the same as the Lie derivative of Y with respect to X. Okay, so this showed up, for example, when we define the Riemann curvature tensor and so on. Okay, so secretly we're using Lie derivatives even there. Okay, so let me just tell you some properties of the Lie bracket. Again, I'm not sure if we showed these, but they're very easy to show from this definition. Okay, you can show that it's bilinear. That is, if I take X and I take two, instead of just Y, I take a linear combination of Y1 and Y2. Then it's bilinear in the sense that it spreads out. Okay, so if these coefficients C1 and C2 are just real numbers, not functions, then it becomes C1 of Lie bracket X1 Y1 plus C2 of X2 Y2. Similarly, if I take X and I replace it by C1 X1 plus C2 X2, and I take the Lie bracket with the Y, I would get C1 X1 Y plus C2 X2 Y. Okay, so this is what we mean by bilinear. It's linear in X and it's linear in Y. Okay, if I split X into X1 plus X2, it becomes linear. If I split Y into Y1 plus Y2, the Lie bracket is distributive. Okay, over that sum. You can also show this easily this property of skew symmetry, that is X Lie bracket Y is the same as minus of Y Lie bracket X. Okay, which implies that Lie derivative with respect to Y of X is equal to minus Lie derivative of X with respect to Y. Okay, and finally, there's something called the Jacobi identity. If I have three vector fields X, Y, Z, if I take the Lie bracket of X, Y and then take Z and take the Lie bracket of those, okay, remember this is a vector field, so I can always take a Lie bracket with another vector field. And now I take cyclic permutations of such a term and I add them all up, then the sum of those is automatically 0. Okay, so that's why it's called an identity. This is called the Jacobi identity. Okay, so here are some other properties, okay, of this Lie derivative or Lie bracket. So if xy belong to the space of smooth vector fields, f is a smooth function on M. So now instead of constants, let me take Lie derivative with respect to fx. Okay, so f is a smooth function multiplied by x, which gives me another smooth vector field. So now it's basically the same that I'm taking fx, okay, which is a vector field, and taking the Lie bracket with the y. Now this is not distributive. Okay, this is not distributive. That is, I can't just pull out the f and write this as f, okay, x, y. You can show rather easily, okay, that this is fx acting on y, which is just fxy, minus y acting on fx. Now, the thing is, if f is not a constant, then y acting on fx is y acting on fx can be thought of as either f with y on x, okay, or y acting on f times x. So this I can club with this, okay, and write it as f commutator of xy. And so when I'm writing things like this, I mean that y is acting on anything that it's an operator. So any function that I stick to the right, it acts on it. This is very similar to what you do in quantum mechanics, right? There's some kind of operator which acts on something. X acts on everything to the right of it, and f is a sort of doesn't act on anything. It's not it's sort of a trivial operator, okay, like an identity operator. I mean, of course, it's a function of where you are in the manifold. So this is f times commutator of xy minus y of f times x. So instead of being distributive, okay, this fxy is not just this, but you also have this extra piece. Okay, this is a smooth scalar function times the vector field x. Okay, so there's an additional correction which is proportional to the vector field x. Okay, so this is f lxy minus y f of x. Okay, so you see that the Lie derivative, okay, which we have defined, is not just equal to f Lxy. There's also this additional correction. Okay, and because of this additional correction, okay, because of this additional term, this Lie derivative is not the same as an affine connection. Okay, if you recall, for our affine connection, again, we defined it as you take two vector fields and it's a prescription. This prescription requires additional structure in the manifold. It requires you to specify a connection. Okay, but once you specify that connection, you can work out del xp. But one important property of this affine connection was that if I have some scalar function like this, then this was equal to f del xp. Okay, in general, okay, the Lie derivative does not satisfy this property, and therefore the Lie derivative does not define for you an affine connection. Okay, so even on a general manifold, you can always define this Lie derivative. Okay, but you cannot define affine derivatives without some kind of connection. Okay, you need some kind of connection. The metric allows you to get one connection, but of course we've discussed that there are other possible connections are also possible. Okay, without a metric. Okay, but the Lie derivative is not an affine connection. It's not this kind of derivative. It's a different type of derivative. Okay, and that's something that's important to realize. Okay, so importantly, you cannot define parallel transport with a Lie derivative. When you had an affine connection, automatically it gets related to the concept of parallel transport. Okay, to define parallel transport, you need a connection, or you need this kind of affine connection, or in a coordinate basis, you need at least Christopherson. Okay, Lie derivatives can still be defined even without having a connection. Is this clear? Okay, so some additional properties. Okay, if xy are smooth vector fields and f is some map from m to n, okay, and then what we can do is x commutator y, sorry, x Lie bracket y is a vector field on m. Okay, now we can use the map f to push forward this vector field from m to n. Okay, so that we can push forward the entire vector field. The claim is that the push forward of this entire vector field is the same as if I had first pushed forward x and then pushed forward y and then taken the Lie bracket. Okay, this Lie bracket is now a Lie bracket on n, on vectors which are in n. Okay, so the claim is that these two things are exactly the same. Okay, so there's a compatibility between this kind of map f and the push forward map f star that it generates and the Lie bracket. There's a compatibility between f star and the Lie bracket. Okay, for any smooth function f. The proof is here, but I won't go over it. Okay, but intuitively the statement should seem to make sense. Okay, let me give you a little bit of a geometric interpretation of this Lie bracket. Okay, so suppose again, the magenta lines are the flow generated by vector field x. The yellow lines are the flow generated by vector field y. So if you start at the point x mu, which is here, and you flow along the vector field x, and you flow in amount epsilon, you will end up here, which is sigma epsilon of x. If you flow along y, oops. If you flow along y, let's suppose you flow in amount delta, then you will end up at tau delta of x. Tau, remember, is the flow due to the field y. Okay, and then now you can ask, okay, suppose I first flow along x, but then I flow along y. Okay, where will I end up? I will end up at tau of delta. Okay, so I flow in amount delta, but my starting point was now sigma epsilon x. Okay, so this is if I first flow along x and then flow along y, I will end up here. Okay, versus if I first flow along y, then I end up here. And now if I flow along x, okay, so I'm flowing exactly the same amounts in both cases. It's just I'm changing the order in which I'm flowing. Okay, in the first case, I'm flowing in amount epsilon along x and then amount delta along y. Now I first flow in amount delta along y and then I flow in amount epsilon along x. Okay, I would end up here. Okay, in general. Okay, and this point is at sigma of epsilon tau delta x. Tau delta x is where I started. Okay, sigma generates the flow in x and epsilon is the amount by which I flow. So the question is, are these 2 points the same? Okay, is the order, does the order of operations, does the order of flowing first along x or first along y, does it matter? Okay, and the answer is it does matter. Okay, and the Lie derivative is essentially a measure of the fact that these 2 points that you end up at are not going to be the same. Okay, or it's the failure of the closure of this parallelogram. The fact that you don't end up at this point in both cases. Okay, the fact that you don't end up in both at this point in both cases is a statement of the Lie derivative being non-zero. Okay, so let's see how that works. So this, in other words, this Lie derivative or this sorry, what is this thing called? The Lie bracket. Okay, the Lie bracket, it measures the non-commutativity of these 2 flows. Okay, the flow generated by the vector field x and the flow generated by the vector field y. Okay, so let's work out first this quantity. Okay, let's work out the coordinates of this point. Okay, so we want to flow starting at the point sigma epsilon x. We want to flow in amount delta. Okay, but sigma epsilon x itself can be written as, if I started at x, then it's the point x nu plus epsilon x nu. Okay, and tau mu itself is going to be this point, which is my starting point, plus now delta, okay, which is the amount that I flow, times the vector y mu at evaluated at this point. Okay, it's the vector y mu evaluated at this point. Okay, which is at sigma epsilon x. Which is x nu plus epsilon x. Okay, so in coordinates, this point tau mu that I ended up here. Okay, the coordinates of this are x mu plus epsilon x nu. This part is from here. Plus now I have this extra contribution. Okay, which again I can tailor expand for small epsilon. So the first part is just delta y mu of x. The second part is epsilon delta times x nu partial nu y mu. Okay, which is this. Okay, strictly speaking, now I've gone to order epsilon delta, which means that I should have kept things at order, and I'm assuming that this the same order. So I should keep things to order epsilon square here, and I should keep things to order delta square as well. But let's not, I mean, all such terms will cancel out. I'm not going to write them out explicitly, but you should, I mean, if you really want to do this carefully, you should keep terms to order epsilon square and delta square. Okay. Okay. So anyway, so this is the where you end up. Okay, so these are the coordinates of this point here. Now, similarly, you could repeat this process, okay, for the other order of the flows. First, you flow this way and then you flow this way. And it's easy to see what would happen in that case. I just exchange epsilon with delta and capital X with capital Y. Okay, and what I would get in that case would be so again, this delta y gets replaced by epsilon x. This epsilon x gets replaced by delta y. And here again, I exchange epsilon delta and I exchange capital X and capital Y. So I would get epsilon delta y nu partial nu x mu. Okay. And now if I compare the difference in the coordinates, so that is I compare the difference between this coordinate and this coordinate. So I take the difference between the two. So I compare the difference between these 2 coordinates. What I would get is all of this cancels out. Okay, and the difference between the two is just epsilon delta times x nu partial nu y mu minus y nu partial nu x mu. In other words, it's epsilon delta times the Lie bracket of xy. Okay, so the fact that these two, the order in which you follow these flows, okay, that matters. Okay, tells you that these flows are incompatible with each other or they're non-commutative. The order in which you flow matters. Okay, and the the difference between the displacement in the coordinates is proportional to the Lie derivative, okay, or the Lie bracket between x and y. So this Lie bracket is a measure of the failure of closure of that parallelogram. Okay, it's either this Lie derivative or this Lie bracket. If both of these are 0, okay, then it means that you will either order of following the flows will end up at the same point. Okay, that is the statement that the Lie derivative is 0 implies that if the Lie derivative is 0 everywhere, it implies that the flows, you can follow them in any order and you'll always get to the same point. Okay, so those are called compatible flows, but in general, flows can be incompatible with each other. Okay, any questions here? Maybe if we have some time, we'll do an example of incompatible flows. Okay, so the next thing we'll do is evaluate the Lie derivative. So we now evaluated the Lie derivative of vectors. Okay, now what we'll do is evaluate the Lie derivative of a dual vector. So again, imagine that we have a vector field x, okay, and we have a dual vector field omega. Okay, so this is a dual vector field, and x is a vector field. So x generates flows, as we've seen before. Okay, so x, the vector field x will take me from, let's say if I start at some point x, it'll take me to sigma epsilon x. And the dual vectors, I have a dual vector at sigma epsilon x and I have a dual vector at x. Okay, and now I can define the Lie derivative by pulling back this omega sigma epsilon of x. So I want to pull this back here. Okay, and the pullback is generated by sigma epsilon is the map that takes me here. Sigma epsilon upper star pulls back dual vectors. Okay, so I pull back this dual vector, I get this dual vector, and I now take the difference between the pullback of this dual vector and the dual vector that is here, that is omega x. So I take the difference between those two, and that defines a Lie derivative acting on, instead of vectors now, it acts on dual vectors. And since the difference between these two, okay, is a dual vector, the result of this operation is not a vector, but now it's a dual vector. Okay, so I now have limit epsilon goes to 0 of sigma epsilon star omega sigma epsilon x minus omega x divided by epsilon. Okay, which is in an equation, it's the difference between this vector and the original vector, dual vector omega x, where omega belongs to the dual vector space. Okay, so this is the definition of the Lie derivative as applied to dual vectors, and this now gives me a dual vector at x. Okay, so if I work this out in a particular coordinate representation, then what I will get is omega mu dx mu. Okay, and I can now define, okay, omega sigma epsilon of x, and then I can take the pullback. Okay, so omega sigma epsilon of x is just omega. So in coordinates, it's omega alpha at x mu plus epsilon x mu. Because this is the point sigma epsilon of x. Then I apply the Jacobian, okay, which is partial x alpha plus epsilon x alpha partial x mu dx mu. Okay, so the Jacobian implements the pullback. Okay, so when I expand it all out to order epsilon, I get omega mu dx mu plus epsilon x nu partial nu omega mu dx mu plus epsilon omega nu partial mu x capital X nu dx mu. Okay, so putting it all together, now I take the difference with the original omega, which is this, divide by epsilon, okay, and take the limit epsilon goes to 0. Okay, these order epsilon square terms drop out in that limit. And what I'm left with is simply this. Okay, so Lx of omega is x in coordinates is x nu partial nu omega mu plus omega nu partial mu x nu dx. Okay, so this is a dual vector expressed in a dual vector basis. These are the vector, the basis coefficients. Okay. Okay, so we've now defined the Lie derivative of vector fields. We've now defined the Lie derivative of dual vector fields. And now we can also define the Lie derivative of just smooth functions. Okay, neither vectors nor dual vectors, just smooth functions. So that's also, you can imagine how you define it. You take the limit epsilon goes to 0, 1 by epsilon f. So if f is a smooth function, you evaluate f at sigma epsilon x. Okay, that is f after you flow, and you compare that with f before you flow, and you take the difference between the two, and you divide by epsilon. Okay, so that is in coordinates would just be this. Okay, which is quite easy to see what that is. It's just x mu of x acting on partial f x mu, which is just x on f. Okay, so it's just your usual directional derivative where the vector field x is acting on f. Okay, so the Lie derivative is just the usual vector field x acting on f. Okay, so this again is a scalar function. Okay, so Lie derivative is always with respect to a vector field. But now we've seen that we can either differentiate a function, or we can differentiate another vector field, or we can differentiate a dual vector field. The result of this operation is either a smooth function, or a vector field, or a dual vector field. Okay, you get back the same type of object that you're differentiating. Okay, any questions about this? Okay, so now what you can do is, in the same natural way, you can extend this concept. Now that you can differentiate vectors and dual vectors, you can also extend the Lie derivative to arbitrary tensors. Okay, the way you do that is first you imagine that you construct tensors as tensor products. Okay, so imagine that I have something which is a tensor product um, of q vectors and r dual vectors. Okay, so this is obviously a tensor of type qr. And now I can define the Lie derivative in a very natural way, right? I have to take vectors and I take the vectors at the point sigma epsilon fx and I pull them back. By pull them back, I mean I push them forward using the inverse map. And I take all dual vectors, okay, and I pull them back using the usual pullback. Okay, and I take the difference between that tensor and the tensor at the point x. Okay, and when I take the difference between the two in the limit epsilon goes to 0, that defines for me my Lie derivative. When I use this to define my Lie derivative, okay, so the claim is, or this proposition, is that that will result in some properties of the Lie derivative. The first property of the Lie derivative is that the Lie derivative of tensor 1 plus tensor 2, where t1 and t2 are tensors of the same type. Okay, it doesn't make sense to add tensors of different types. So you add tensors of the same type, then this Lie derivative will be distributive over those. So it's equivalent to taking the Lie derivative of t1, which is a tensor of type t again, plus Lie derivative of t2. Okay, so the claim is this property will automatically follow. And the second property that will follow is that Lie derivative of, if I have now two tensors and I take the tensor product between them. So if I take t1 cross t2, for example, if this is a vector and this is a dual vector, then now I have a tensor of type 1, 1. Okay, then the claim is that this will be again distributive in the sense that first I will take the Lie derivative of t1, okay, tensor product with t2 plus t1 tensor product Lie derivative of t2. Okay, where these t1 and t2 are tensors of arbitrary types. Okay, so they don't just have to be vectors or dual vectors, they can be tensors of arbitrary types. Okay, so these rules will follow from this intuitive definition of the Lie derivative through tensor products. Okay, so let me just show you an example of how you would evaluate this. So for example, suppose we take a vector field y belonging to the space of vectors and omega belonging to the space of dual vectors. Let's construct the tensor product y tensor omega. So we'll take y tensor omega and evaluate it at the displaced point, that is sigma epsilon of x. Okay, and now what we can do is this is now x, this is sigma epsilon of x. And now we want to take this tensor, which is at this point, and bring this tensor back to this point. So what do? Well, we pull back vectors and we pull back dual vectors. Okay, so we can pull back dual vectors using this. We can pull back vectors using the inverse map and the push forward. Okay, so that's this. So we implement these two operations on y tensor omega at sigma epsilon x. And yeah, so which is basically we say we push forward by using the inverse map, we push forward y and we pull back omega. And then this gives us a vector at x. Okay. Okay. I mean, maybe I'll just leave this in the notes, okay, and you can go over the notes later. But you can show that basically with this definition of the operation, okay, so now I define the Lie derivative as this object, okay, minus the original tensor y tensor omega at x. Okay, so whatever original tensor I had at x, I subtract that off. Okay, then what you can do is you can show, for example, all of these, this property, okay, this property that we argued here. Okay, for the tensor products. Okay, that is, you can show that you get something like y tensor product Lx omega plus Lxy tensor omega. Okay, can you tell me what type of tensor this is at the end of it?
1, 1.
Yeah, at the end, if you started with y omega, okay, and it took the tensor product, that was a tensor of type 1, 1. So now if I take the Lie derivative of that, I'm also going to get a tensor of type 1. Okay. Yeah, so now what you can do is you can use these propositions. Now that you've defined, the Lie derivative on tensor products, you can now use this to define the Lie derivative on any general mixed tensor. Okay, because any general mixed tensor T can be written as some basis coefficients times dx mu dx partial x mu. Okay, and now this is a product of some number of vectors and some number of dual vectors. And we now know how to differentiate a tensor product like this, okay, using these rules. Okay, so what you will find is the Lie derivative, okay, of this type of tensor, for example, the 1, 1 type tensor, will be, okay, again, it's a lot of math, so I won't work it out. Okay, at the end of it, what you get is something like this in components. This 1, 1 type tensor. So what you will get is first I'll take x, I'll have x alpha partial alpha, and then the tensor coefficients, okay, t mu nu. So again, I'm expanding in the basis dx mu partial x mu. So the first thing is you'll have something like this. Okay, the vector like indices. So if t was something like t mu nu, these are vector like indices. Okay, so for every vector like index nu that I have, sorry, this alpha that I have, I will replace that by a dummy index. Okay, and then I will take a derivative with respect to the dummy index of x nu. Okay, and I will put the index nu over here. And similarly for every dual vector like index, okay, so that is this one in this case, I will differentiate with respect to the dual vector index, and I'll put a dummy index for t and a dummy index over here and so on. Okay, so this and these, the dual vector indices, they will come with a plus sign. This will come with a minus sign. Okay, this is a general rule. And so if I want to generalize this to arbitrary tensors, I've written the formula somewhere down here. Let me just show you. Yeah, so the Lie derivative of an arbitrary tensor looks like this. Okay, it's x mu, where I take the derivative of the tensor coefficients, okay, alpha 1 through alpha q. So this is a tensor of type QR, Q vector-like indices, R dual vector type indices. So I first differentiate the tensor coefficients, okay, with x mu. Then I subtract off, okay, T alpha 1 dot 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 alpha q. One of the vector indices gets replaced and it comes with a derivative, okay, partial rho. And what does it differentiate? It differentiates x, where x is the vector by which I'm taking this Lie derivative, alpha I. Okay, and so this is the alpha I which got replaced by a rho here. And I do this for every one of these indices alpha 1 through alpha q. And then I also do something similar for the dual vector indices. And so all these ones where I replace the vector indices, they come with a minus sign. All the ones where I replace the dual vector indices, they look like this. So it's tensor alpha 1 through alpha q, beta 1 through beta r, but one of the betas gets replaced by rho. I differentiate with respect to that particular beta. I differentiate x rho, okay, and I sum over rho. Okay, and I take this rho in all possible positions. Okay, so this represents q possible terms. This represents r possible terms. Okay, r possible terms after doing the summation over rho. And then this is a tensor. These are the tensor coefficients. Okay, and it's a tensor coefficient of something with alpha 1 through alpha q vector-like indices and beta 1 through beta r dual vector-like indices. Okay, so this is the general form of this tensor. This formula is not there in Nakahara, okay, but it's quite easy to work out. Okay, it's not easy, it's a bit painful, but you can work it out, okay. Okay, and finally there's a theorem, okay, which is an exercise in Nakahara, and again, this is a bit tedious to work out in components, okay, but you can try this out. So if I take the Lie derivative with respect to the Lie bracket of xy, so the Lie bracket of xy again returns for me another vector field. So I can always take the Lie derivative with respect to that. And if I differentiate a tensor with respect to that vector field, then this is the same as first take the tensor field and take the Lie derivative with respect to y. Excuse me. Then take the Lie derivative with respect to x. And do the operations in reverse and subtract that. Okay, the claim is that these two things are equivalent. Excuse me. Okay, the proof again is in these notes, but it's very tedious, so I'm not going to discuss it. Okay, the result is more important. Any questions? Okay, so let's just summarize, okay, what we've learned in the last 3 lectures. Okay, so the first thing we learned is that if you have a manifold M and you have a manifold N, and if I have a smooth map F, which takes me from M to N, then what I can do is not just have these maps from M to N, but I can also push forward vectors using an induced map called F star. And I can pull back dual vectors using an induced map called F upper star. And what we've seen is if F is a diffeomorphism, which means the inverse map also exists, then you can use this inverse map to pull back vectors and you can push forward dual vectors. Okay, so that was what we did in this 2 classes back. Then in the last class, what we did was to say if you have a manifold M with some vector field X, okay, so some vector field X on this manifold, then this vector field X can be thought of as generating flows on M. Okay, and X generates one parameter diffeomorphisms, where a point with coordinates X, okay, gets mapped to coordinates e raised to t X acting on X, okay, where this X is the vector field X. Okay, so X we call capital X is called the generator of diffeomorphisms, and T is the parameter by which you flow. And if you have an infinitesimal T, let's call it epsilon, then X mu becomes X mu plus epsilon X mu of X. Okay, so that's what we did in the previous class. And today what we did was to look at the Lie derivative. Okay, that is, and the most general result we showed is that if you're given a tensor field T, okay, this tensor field T is some tensor field over the entire manifold. So you have a manifold M, there's a tensor field T, and you have a vector field X. Okay, the vector field X generates a flow, and what you can do is you can define the Lie derivative, Lx of T, which is also a tensor of the same type as T. Okay, so this Lie derivative results in a tensor of the same type as T. And in components, if your tensor is of this type, T alpha 1 through alpha q, beta 1 through beta r. So if it's a tensor of type QR, then this is the Lie derivative. Okay, this is that formula which I showed you, which looks complicated, but you see that there's actually a neat structure to it. Okay, and in the special case when this tensor field is also another vector field, okay, then this Lie derivative Lxy, it measures the incompatibility of the flows generated by X and Y. Okay, or in other words, it measures under if I first displace by X and then by Y, or I first displace by Y and then displace by X, it measures the failure of closure of the parallelogram, the fact that I don't end up at the same point when I follow these flows in different orders. Okay, so this Lie derivative of two vector fields, okay, of the vector field Y by X is equal to the Lie, what we call the Lie bracket of XY. And this Lie derivative is not an affine derivative. Okay, it's not an affine derivative in the sense that L of fxy is not the same as flxy. We saw that there's this extra piece, y of fx. Okay, this extra piece, and that's why these are not equal. And therefore, it cannot. This Lie derivative is not something that you can use to define parallel transport. Okay, and finally, we saw this last property. Okay, which is that the Lie derivative with respect to the Lie bracket of xy of some tensor field T is, let me first take Ly of T followed by Lx. Then let me first take Lx of T followed by Ly, and let me take the difference between the two. Okay, that these two things are equal. Okay, we didn't prove this, but you can show it. Okay, any questions at this point? The last thing I want to do is one example just to show you how all of this works.
Sir, one question. Like sir, when we have a map from one manifold M to another manifold N, like unless we have F inverse, we can only push forward vectors and pull back dual vectors. But sir, like if there is some other function which is not F inverse, let's say some H, which is a function from N to M. Then we can define we can define pullback of vectors from N to M. Like then there will be a curve like so.
Yeah. So okay. So let's write that. So if you have M, you have N. Okay. F will, if I have a vector here, it'll push forward to a vector here. Right?
Yes, sir. Yes. So now let's say we have one mapping from N to M. Yeah. G.
Yeah. So now let's say this is a vector. Now let's suppose there's a vector here. Okay, this will generate vectors here. Okay, through the map G star, and this is through the map F star. Okay, it's taking me from V to V prime.
Yes, sir. And then my question is like, sir, now if we let's just start with V prime, which is actually F star of V, but if we start with V prime and then if we act G star on it, we don't get back to V because G is not F inverse.
Yes.
Yeah, so is that the reason why we don't talk about the reverse thing, like a pullback of vectors, like unless we have F inverse, because this mapping will not be will not be unique, because we can always have a mapping this way.
Yeah, you need to specify the second mapping, right? Basically, if I only give you one mapping, then there's no unique way to get this. So basically what you want to do is through G star, I want to get this, right? I mean,
Yes, sir. Yes, sir. Like, so V, like G star acting
should be another vector here, right? So this is G star of V prime, which is G star of F star of V, right?
Yes, sir. So, sir, unless G is equal to F inverse, we don't get back the same V. Like, so is that the reason we like in the first class, like we didn't talk about like unless F is a diffeomorphism.
It's more than that, right? See, the thing is, it's not just that you want to be get a vector on M. You need to be back at the same point on M if I want to compare those vectors.
Yes.
Otherwise, they live in different tangent spaces.
Hmm.
So unless it's exactly the inverse function, then I'm not coming back to the same point in M. Right? Only the inverse function will take me back from F of P to P. And then I can compare, this push forward with the original vector.
Yes, sir. Yes, sir.
Right. So basically, it's special to use F and F inverse because you're talking about comparing. You're not just have diffeomorphisms which take you back and forth, from one point on M to another point on M, but they also allow you to compare tangent vectors, different tangent vectors at the same point. Okay, which are induced by these pull forward, pull back and push forward maps.
Yeah, like a V and F inverse star V primed both lie on the same point on M.
V and F inverse star
Of V primed.
Of V prime, yeah, where V prime is
Equal.
F star V. Right? This vector and this vector both lie at the same point on E. And they belong to the same tangent space.
This can only happen like if we have F inverse, and if we have G, then this will not happen.
Yeah. Okay, so let me just end with an example. Okay, so we'll do an example of incompatible flows. Okay, so here are two flows. Okay, in two. So let's imagine that our manifold is R2. Okay, and we have these two flows, R because it generates rotations, and T because it generates translations. Okay, so if I plot this R, we have done this before. R looks like this vector field. Okay, something like this. Okay, I'm just plotting the directions here, but the directions look like this. Okay, so the streamlines of this, as we discussed in the last class, look like this. Okay. So a point here will circulate around like this. A point here will circulate around like this. And T is partial x. Okay, so that generates translations in the x direction. So T looks like this. Okay, so the streamlines are like this. Okay, so the flow is to the right in this case. Now these two flows are actually incompatible with each other. Okay, so that means that if I first rotate okay, by some parameter theta. So that means I rotate by an angle theta. Okay, or I translate by an amount a. That is, I move forward in the x direction by an amount a. Okay, so let's imagine that I first perform the operation of rotating and then I translate. That the result of those two. Okay, so first rotation followed by translation. This operation is not going to be the same as first translating to the right and then rotating. Okay, so any point that I first rotate and then translate, that's not the same as first translating this point and then rotating it. Okay, there's a failure of closure of this parallel. Okay, so let's see why that is. Okay, or let's just see mathematically how to work with all the we had some very complicated notation, but let's see how to work with it. Okay, so I'm going to skip some minor details here, which are relevant for the proof, but let me just come to this formula, okay, which we kind of written down earlier. Actually, to show this, we needed a couple of more steps, which I've written again in the notes, but I'm not going to work out. So if I want to know the coordinates of the point that I am, assuming that I start at some point x, I flow by an amount t, and I want to know where I am. Okay, what are the coordinates that I'm at? Okay, which are sigma mu tx. This we said is exponential of, if I flow with some field x, it's exponential of tx of x. Okay, to show this was a little bit of more work from what we actually derived in the last class. Okay, but the derivation is here. But let's we'd written down this formula. Okay, so we'll work this formula. So now let's assume that we have, instead of trying to be very specific to the case where we're trying to just find out what happens to our coordinates, let's take a general function f of xy. Okay, and let's ask what this operator does. So we can think about this operation separately from the fact that we're trying to actually transform our coordinates. Okay, so let's imagine that we have a general function f of xy rather than just x mu. Okay, and let's assume that we act with e to the at. So a is like your time parameter. It's the amount by which you're translating, and t is this translation operator or translation vector field, which is this one, partial x. So this is e raised to a partial x acting on f of xy. Okay, and then you can do a Taylor series expansion of this e raised to a partial x, f of xy plus a partial x f xy plus a squared by 2 factorial partial x f xy. Okay, okay, so at sorry, this is holding y constant. Okay, and then I evaluate the derivative at x. Okay, and what you will get at the end, it's quite easy to see. This is just f of x plus a comma y. Okay, and this you will recognize from quantum mechanics as just your translation operator. Okay, e raised to a partial x. Okay, and so this is just your translation operator. Okay, and acting on f of x y, it just does this. Okay, in quantum mechanics, your translation operator is something like this: e raised to minus I p dot p hat dot x p hat dot a. Okay, and p hat is by h bar. P hat is minus I h bar partial x. Okay, so if I plug this in here, what I have is e to the product. I get a plus sign, I square. Okay, it depends on whether I'm doing an active or a passive transformation. Let's just say it's something like this. E to the a partial x. Okay, so this operator just gives me this. Okay, quantum mechanics, and it's the same thing here. So this operator acting on the wave function, okay, will take me to the wave function psi of x plus a. Okay, and so any function on the manifold, okay, that could be a wave function, could be any other function, okay, will get translated by this operator. Okay, it will get translated by this operation. Okay, so this operation basically, in the case where x is this translation operator, this one, okay, translation in the x direction, it basically generates translations. And so in particular now, if I choose these functions to be coordinate functions, so if I choose them to be like we've done here, if I choose them to be coordinate functions, if I choose them to be just the x coordinate or y coordinate of my starting point, So if I say that x is the x coordinate f of xy is x, or if I choose f of xy as y, so it just chooses them to be starting points, then EAT acting on x will give me x plus a. EAT acting on y will just give me y. Okay, in other words, the new coordinates of the point xy become x plus a comma y. Okay, under a translation. Okay, similarly, under a rotation, you can show that e to the theta r f of xy is this e to the theta of this operator. Okay, acting on f of xy, and you can show that this basically will give you something like a rotation. Okay, it'll be f of x cos theta minus y sin theta x sin theta plus y cos theta. So xy get rotated to this new coordinate. Any function of xy when I act with this operator gets rotated to f at the rotated coordinates. Okay. Yeah, and now what we can do is we can take those vectors, vector fields r and t. Okay, we can work out the mu component of the Lie bracket. So this is just r nu partial nu t nu minus t nu partial nu r nu. No, sorry. This is t nu. Okay, now you remember that the t itself was just partial x. Okay, which means that the basis coefficients are xy independent. Okay, the basis coefficients are xy independent. So therefore, this term is just 0, okay, for this particular r and t, but this one is non-zero, okay, because r has x-dependent coefficients. Okay, r has xy dependent coefficients. So when I differentiate this with respect to x, okay, this will be non-zero. So what I get is minus t nu partial nu r mu. Okay, which is going to be this t nu is t nu partial nu is just partial x. Okay, which I've written here. There's a minus sign. And now if I take the y component of r mu, that is if I take the y component of r of this commutator, so this Lie bracket, rty, it's minus partial x acting on x, which is minus 1. Okay, so the fact that these two are the Lie bracket is non-zero means the flows are incompatible. That is, the flows do not commute. Okay, so the order in which I do the operations, whether I rotate first or translate first, okay, it matters. Okay, and I can't do them in reverse order and get the same result. So these two operations of rotation, okay, and we've seen this rotation can act not just on the coordinates, it can act on any general function of the coordinates. Okay, and similarly, you have a translation which can act on general functions of the coordinates. So similarly to quantum mechanics, okay, you have this Baker-Campbell-Hausdorff formula, which you might have seen. If I have two operators A and B, okay, then e raised to A, e raised to B is e raised to A plus B plus half commutator of AB. In this case, it would be Lie bracket of AB plus 1/12 A comma B plus B comma B comma A. Okay, and so on. It's a big series. But in the case where A comma B is just this Lie bracket is just a number, okay, which commutes with everything. So in this case, this is called a central Lie bracket. Okay, that is, it commutes with r and t. In that case, all these other terms vanish. Okay, and you just have this term. Okay. So in this case, what you would have is that this center, this is in the center. So AR comma theta t would just be, I'll pull out the A and theta, and what I get is this minus 1. Okay, so I get plus half minus 1, and only the y component is non-zero, so I get this operation, minus half partial y. Okay, so this t, remember, is a derivative operator. This r is also some derivative operator. So this product, okay, sorry, this product, e to the theta r, e to the at, is some operation like this. And if I change the order of these two, okay, then I change the order of these two. Okay, and the fact that they don't commute, and also we've seen if you change the order of those two, then you basically get an extra minus sign. Okay, the Lie bracket picks up an extra minus sign. So these two operations are not the same. So this order of doing operations is not the same as this order of doing the operations. Okay, these two don't commute. Okay, and these flows don't commute, or they're incompatible flows. Okay, and you can check quite easily that again you can perform the operations on x. Okay, so a translation on xy takes you to x plus a comma y. A rotation on xy. Okay, again because this rotation is about 0, 0. Okay, it takes you to the point x cos theta minus y sine theta, and y sine theta, sorry, x sine theta plus y cos theta. Okay, so now if I first translate and then I rotate, okay, the point that I will end up with, so if I first translate followed by rotation, then I will end up at the point x plus a cos theta minus y sine theta, and x plus a sine theta plus y cos theta. Okay, this is where you'll end up. But if I first rotate and then I translate, then I will first rotate, I will get this, and then I will translate. So I'll get x cos theta minus y sine theta plus a, x sine theta plus y cos theta. Okay, so these two are not the same, and that's why the order of operations matters. Okay, the order, precisely because your rotations are not shifting. The operation of rotations is centered around some particular origin. That origin of rotations has not changed. Okay, the translation is only acting on the on the points that you're moving forward. Okay, so that's what you mean by incompatible flows. Okay, so I hope this example made it a little more concrete what we are doing. These are naughty. Questions?
So this is actually like the incompatibility of LZ angular momentum and px.
Exactly. This is in quantum mechanics. You would say that LZ px. LZ can be written as xpy minus ypx. Okay. Px commutes with x. Px commutes with y. Px commutes with px. So this is just x py comma px. But since it commutes with py, I can just pull a py outside this commutator, and I would have x comma px py. And the fact that these two don't commute is going to give me something like I h bar py. Okay, yeah, so it is indeed very much related to the non-commutativity of LZ with px. Okay, and that's what we saw also, right? This is partial y, and that's exactly the extra term that we got here, okay, from the non-commutativity of rotations and translations. Okay, let me just stop the recording here.